Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the ferrous and non-ferrous materials. So, what is a ferrous and what is the difference between these non-ferrous materials? So, generally, metal alloys by virtue of its composition. So, any type of material can be described or can be classified depending upon the composition. So based upon the compositions, these materials have been classified into ferrous as well as non-ferrous materials. So generally, these alloys by virtue of its composition are classified into two categories. So those two categories are nothing but the ferrous and non-ferrous materials. So what is a ferrous element or ferrous materials means? So ferrous alloys in which there is a rich percentage or maximum percentage of iron as a principal constituent, then those elements or then those materials are called as a ferrous materials. Similarly, in the non-ferrous elements, so what is happening? There is a less percentage of carbon content. Okay, then those are called the non-ferrous. So what is the main difference between these ferrous and non-ferrous materials is, so ferrous materials in which iron is the maximum constituent. So if iron is a maximum constituent in that material, in that alloy, so then it is called as a ferrous. So which includes steels and cast irons. So steels and cast irons are some of the examples of these ferrous materials. And coming to the non-ferrous alloys, so what are the? They are not based upon iron. So maximum there is no based upon the iron. Then those type of materials are called as a non-ferrous materials. So ferrous alloys. So we have discussed there should be a maximum percentage of iron. So principal concentration is iron-based components, that is called as a ferrous. So here iron is the principal constituents are produced in large quantities. Then those type of materials are called as a ferrous. So wherever you find the maximum percentage of iron, then those are called the ferrous materials. And these are especially important in the engineering construction materials. And these are very widespread in used upon the application. Depending upon the applications, these ferrous materials have been again classified. So first one is the iron containing compounds. So wherever the iron containing compounds are there, so that will be existing in abundant quantities in the iron crust. Next is the metallic iron and steel alloys may be produced using relatively economical extraction, refining, alloying and fabrication techniques. So these are some of the importance of these ferrous material. That's why we are going with the ferrous materials in a wide applications of mechanical engineering. And similarly, ferrous alloys are extremely versatile. Why? Because they have a lot of mechanical properties. So any material which is having n number of properties that can be very useful in the mechanical related applications. That's why most of the mechanical related applications, even the construction of the bridges, all these heavy equipments, heavy machinery, all these are being manufactured with the help of these ferrous materials. So since these are having very extremely versatile properties as well as that can be tailored into a wide range, so it can be manufactured, it can be tailored in any type of formation. So these are some of the main advantages of these ferrous materials based upon the mechanical and physical properties. These are being widely used. So if you go to the classifications of these ferrous alloys, so generally a metal alloy is being classified based upon the composition. Now what is the metal alloy here? So metal alloy is the main material. So this metal alloy again it is being classified into two categories. So what are the two categories? That is ferrous and non-ferrous. So in the ferrous in which we have a large composition of iron, that's why it is called as a ferrous. And coming to the other category, you have non-ferrous which is having less, that is it is not based upon the iron composition. So that is the non-ferrous element. So that's why this metal alloy is being classified into ferrous as well as the non-ferrous. Again these ferrous are being classified again into two categories. So what are those two categories here? Steel and cast iron. So these ferrous again it is being subdivided into two classifications, that is steel and cast iron. how we are dividing these, how we are segregating these, how we are differentiating means based upon the composition only. So that's why in the previous sessions we have discussed how to identify the composition. Depending upon the composition, these ferrous as well as non-ferrous elements are being classified. And again, the subdivisions are also being classified based upon the composition. Even 1.1% change in the composition varies the physical properties and varies the microstructure. So depending upon these, the materials have been classified into different types of categories. Now, the ferrous is being divided into steel as well as cast iron. Now, steel is again having low alloy as well as high alloy. Again, steel is having low alloy and high alloy. So what is again low alloy? In low alloy again we have low carbon, medium carbon and high carbon. That means percentage, even in the low alloy, how much percentage of carbon is there. So based upon the percentage of carbon, again this low alloy has been divided with low, medium and high carbon. So like that, we are differentiating, we are segregating all these things based upon the composition of the carbon content. And coming to high, you have here tool and stainless steel. So again, these are again classified based upon the composition. Now again, the low carbon is having plain and high strength alloy, and medium carbon is also having plain and heatable treatment, and high carbon is having plain and 2. So depending upon the properties also, these steels have been subclassified or subdivided. Now coming to the other side of the ferrous, we have cast irons. So what are the cast irons in which we have grey cast iron, ductile or nodular cast iron, white cast iron, malleable cast iron and compacted graphite iron. So like this, each class being divided into different categories based upon the composition of the weight percentage of different compositions. So like that, a base metal alloy, the first one is this metal alloy. This metal alloy is classified into two categories based upon the iron content. So if you are having higher number of percentage of iron, then that is called as a ferrous. If you are having less percentage, or if it is not based upon the iron content, then that type of materials are called as a non-ferrous materials. And these ferrous materials are again subdivided into different categories based upon the how much carbon content is there. It is divided into steel as well as cast irons, and cast irons again divided into 5 categories. And these steels are again based upon the carbon content, low, medium and high carbon content. And again based upon the properties, it is again subdivided into different categories. So like that, we have to differentiate. Each element will have its own properties, its own microstructure, its own compositions. So based upon these things, we are trying to nomenclature these materials. Now, as we have seen the different classifications, so what is a steel which is being classified from the ferrous materials? So steel are iron carbon alloys that may contain appreciable concentration of the other alloying elements. So in the steel, which have been iron as well as carbon alloys, in which we have another alloying element. So another adding elements are being there. So there are thousands of alloys that have been different compositions. So small variation in the compositions on the base element are called the alloyings. So we are adding some other improvements to enhance the properties or enhance the physical as well as the mechanical properties. We are trying to give some additions. So those are called the alloying elements. So to the base element, we are trying to give some new elements or alloying elements to enhance or to improve the mechanical as well as the physical properties. So in this steel also, since it is a iron carbon alloying element and it is having more number of another elements or more number of any other alloys, this can be increase the mechanical properties. And this alloying, how we are trying to do? We are trying to do in different methods like a hot working or as well as cold working process. So we can't directly add the alloys into the base element. So during the heat treatment process, you have to heat the element. So once you take the raw material, so this raw material has to be heated to the recrystallization temperature. So after reaching that recrystallization temperature, these alloys has to be added. Then only we can do the alloying or addition of the alloys into the base element. So while adding these, what is happening? We are trying to improve the quality, improve the properties of the given steel. So mechanical properties are very sensitive to the content of carbon. which are more less than 1 percentage weight percentage. So you're having very less percentage of carbon, that is approximately 1 weight percentage of carbon. And some of the more common steels are also classified based upon the carbon concentration. So that's what, depending upon the how much percentage of carbon is available. So based upon these percentage, we are again classifying the steels into different categories, namely low, medium and high carbon types. So as we have seen in the previous slides, how we are trying to define or how we are classifying these steels means based upon the carbon content. So in generally we have very less percentage of carbon in the steels. Now based upon the carbon content, again the maximum is 1%. So if you vary these 1% according to the percentages, we are classifying again the steels into low carbon steel, medium carbon steel and high carbon steel. So that's what you have to classify based upon the composition. So if you go with the low carbon, so what is the range of this low carbon means? Steels are again iron carbon alloys that may contain appreciable concentration of another elements. So the mechanical properties are very sensitive in this case, and also we are having very less percentage of this carbon content. Now, of all these different steels, those produced is the greatest quantity and which follow in the low carbon classification. So whatever in the name itself we have low carbon, that means we have very less percentage of carbon. So based upon the less percentage of carbon, we are classifying the steels. So what is how much percentage means it is 0.2 weight percentage of carbon. So generally the steels which are containing very less percentage of carbon, which is approximately 0.25 percentage of carbon, and are unresponsive to heat treatments. So instead of martensite, strengthening is accomplished by cold working process. So generally, if you want to do any alloying, you have to do the heat treatment process. So any element which is not responding to the heat treatment process, those types of elements or those type of steels are called the low carbon steel. So in this case also, since we have very less percentage of carbon, that is 0.258 percentage of carbon, this is not responding to the heat treatment process also. So that's why this can be accomplished by the cold working process. So since it is not responding to the heat treatment, so we are going with the cold working process. So generally any metal or any steel, it responds to heat treatment, but in this case, since you have very less percentage of carbon, so this low carbon steels are not responding to the heat treatment process. That's why we are going with the cold working process. And the microstructure consists of ferrite and pearlite constituents. So if you go to the microstructure of the low carbon steel, so if you have the compositions of ferrite as well as pearlite structures in this microstructure of the low carbon steel. So that is what we have to identify based upon the composition of weight percentage of carbon. So low carbon steels are having 0.25 weight percentage of carbon, less than 0.25 weight percentage, and this is not responding to the heat treatment. That's why we are going with the cold working process. And one more thing you have to remember is that the microstructure is constituting both pearlite as well as a ferrite in this low carbon steel. And because of that, these alloys are relatively very soft and weak, but have outstanding ductility and toughness. So because of the less percentage of carbon, so what is happening? So these are having very soft and weak in nature. If you go to the physical and mechanical properties, so since the carbon percentage is very less, so these are tend to very weak as well as soft type of things. And another advantage of this is you have a good ductility as well as toughness. So these are some of the advantages as well as the disadvantages when you see with these low carbon steels. And in addition to this, what is the other benefits you have is they are machinable, weldable, as well as all steels are at least the expensive to produce. So though it is very soft as well as weak in nature, what we can do the machining process. Since it is very soft, it is easy for machining. Any type of manufacturing we can do with this type of material, as well as it can be easily welded also. You can do the welding process with this low carbon steels, as well as all of steels are the least expensive to produce. So these type of low carbon steels are very expensive to produce. And typical applications, so if you go to the applications, so it include automobile body components, structural shapes like I-beams, channels and angle rows, and sheets that are used in pipelines, buildings, bridges and tin cans. So these are some of the applications. So if you go to the mechanical and physical properties, what you are having with the low carbon steel, we have very soft in nature as well as it is very weak. And coming to the ductility and toughness, it is having a good qualities of ductility as well as toughness. And in addition to these low carbon steels can be machinable and it can be welded, and of course it is very expensive to produce. And after this, whatever the applications we have with the low carbon steels, it can be done with the body parts of the automobile components. And if any sections has to be done, like I-beams, I-channels, angle rows in the construction of the bridges, these low carbon steels can be used. As well as these low carbon steels can be used in the pipelines, buildings, bridges and tin cans. So these are some of the examples. So each element it has its own properties as well as its own applications. So no material can be replaced the other material. So that's why it is its individual properties as well as individual applications. And coming to high strength and low alloy. So another group of low carbons are high strength, low alloy, that is HSLA steel. So these are called, which is having, though low carbon alloy is there, but it is having high strength. So they contain other alloying elements such as copper, vanadium, nickel and molybdenum. So that's why by adding some impurities, by adding some alloying elements, you can enhance the properties. So in the previous case, you have only 0.25% in the low carbon steel. So for the same low carbon steel, if you add some alloying element like copper, vanadium, nickel and molybdenum, what is happening? It is improving its strength because of some addition of some alloying element. So that's why if you want to increase the properties, you have to add some another alloying element for the same element. So the strength is increasing by adding these copper, vanadium, nickel as well as the molybdenum. So what is happening here? Combining all these things, it is the concentration is as high as 10 weight percentage. It is increasing from 0.25 to 10% strength. It is increasing. That's why possessing high strength, that the plain low carbon steel. So though it is a low carbon steel, but it is having high strength because of adding some alloying elements like copper, vanadium, nickel and molybdenum. So most may be strengthened by heat treatment. Now this can be done, this can be reacted with the heat treatment process and giving a good tensile strength approximately around 480 megapascals. So like that. So in the previous slide, we have discussed only about low carbon without adding any other alloying element. Suppose for the same alloying low carbon steel, if you are adding some copper or vanadium, so what is happening? It is increasing its strength up to 10%, as well as it is giving a maximum tensile strength up to 480 megapascals. So though you apply a force, tensile force, it can be withstand up to 480 megapascals. So like that, you are increasing the properties by adding some alloying element. That's why alloys are very important in order to increase the physical as well as the mechanical properties. And in addition to this, they are very ductile, formable and machinable. So though you are adding this, it is not changing anything. So it is again increasing. Rather than this, it is increasing and it is very ductile and it is very formable and it is easy to do any shape, and any machinable process also we can done with the help of these types of high strength low carbon alloys. And again, in normal atmospheric conditions also, these steels are more resistant to corrosion. So this is very important. So corrosion resistance, every material should be free from corrosion. So most of the materials will not be free from corrosion, since if it is exposed to some environmental condition or atmospheric conditions like cold or any chemical exposures, so what is happening? Rust formation, corrosion formation will start. So this has to be resist. So any material, if the life cycle has to be increased, means the corrosion resistance should be very high. So for these type of materials, the corrosion resistance is good because we are adding some alloying elements. So it will increase the corrosion resistance value. So that's why these high strength alloys, high strength low carbon alloys are very corrosion to resistance that the plain carbon steels when you compare with the very plain carbon steels. And again, these have been replaced in many applications where structural strength is critical. So the low carbon steel has its own applications, but once you add some alloying elements, what is happening? It is again increasing some applications. We are trying to add some applications based upon the adding of the alloying elements. So what are those? Again, in bridges, towers, support columns in high-rise buildings and pressure vessels. So again, we are getting some other improvements in the applications also when we add some alloying element. So like that, depending upon our applications, we try to reconstruct the material. So just we can't take the same material. We have tried to do some research and we have tried to identify what are the properties. Can we increase the properties? So depending upon the increase in the properties, we can also use that material to the required applications. So like that, we can add upon alloying elements to that, and we can improve the properties as well as we can apply it to the required applications. So like that, you have to think and identify those things. And now coming to the compositions of these 5 plain low carbon steels and 3 high strength low alloy steels. So what are the things we have? So again, all this has to be segregated depending upon the compositions. How the composition is varying. So based upon the compositions, we are trying to give the names to them, and based upon the applications. So designations, these are the numbers we have to give for the composition based. So 1010 and UNS number is G101000 for the plain carbon steel. So we have the carbon content as 0.10 in this case, and magnesium is 0.45. So like that, depending upon the compositions, how the compositions are being varied and how the different types of alloying elements are being added, we are classifying all these plain low carbon steels. So based upon these compositions, and any other addition of copper or silicon, if you add, still we are increasing the properties. So based upon those compositions, we are trying to give the unique number as well as the grade of that steel. Similarly, if you go with the high strength low alloying steel, so here we are trying to increase the percentage of carbon slowly. So it is, if you see the plain, you are having only up to 0.10 like that, but here we are adding 0.28 and here 1.35 of magnesium. So like that, we are trying to increase the compositions and we are trying to see what is happening. So what is happening here? It is increasing its strength. That's why it is called as a high strength and low alloy steels. Though it is a low alloy, we are trying to increase the strength by adding some alloying element. So we are adding here 0.28 percentage of carbon, 1.35 percentage of magnesium, and 0.35 percent of silicon, and 0.2 percent of copper. So like that, we are trying to add different compositions in order to increase the properties. So based upon those compositions, again, these are classified into 1, 2, 3 steels. That is A440, A633 grade E, and A656 grade E. So all these are being classified based upon the compositions. So any material which is available in the market has some unique number. So what is that unique number? Based upon the compositions, we are trying to give the unique number. And again, based upon all these compositions, you are having some mechanical properties. And based upon these mechanical properties, we are trying to apply them to the given application. So like that, we have to categorize every element. And if you see the same for the same material, what are the mechanical characteristics during the hot rolling process of the material, and typical applications for the plain low carbon as well as the high strength low alloy steels. So for the same previous code 1010, we have the tensile strength as 3.25 megapascals. So up to that tensile strength, it can withstand, it can resist up to 325 megapascals. Similarly, yield strength for the plain low carbon steels, it is 180 megapascals, and ductility is 28 mm. And what are the applications of that 1010 steel is in automobile panels, nails, and wires. These are some of the examples. So like that, based upon that composition, so what are the compositions we have seen in the previous slides? based upon the compositions, you are getting some enhancement in the mechanical properties. So based upon these mechanical properties, we have decided some applications. So like that, everything is interrelated to each other. So starting from the classification, the carbon content percentage, composition percentage, the mechanical properties, and later the application. So like that, everything is interrelated. And if you see the A36 type of low carbon steel, what you are having here, there is some improvement in the tensile strength, that is at 400 megapascals you are getting, and the yield strength is 220, and the ductility is 23. And what are the applications for these type of A36 steel means? It can be used in structural bridges and buildings. So like that, changing in small percentage change in the compositions, the applications vary. And again, if you see the grade 70 with A516, there is a huge improvement in the tensile strength, that is 485, and the yield strength is 260, and coming to the ductility is 21. And where can you use this? Low temperature pressure vessel. So even for the conditions of the temperature also, as well as the pressure, if you want to work any material under high pressure or high temperatures, so how can you decide? Based upon these classifications, based upon these compositions. And suppose the same thing, it has to be applied in low pressure conditions and low temperature, then you have to use this A516 grade 70. Like that, depending upon the applications, you have to select what type of material you can use for the application. Now coming to the same high strength low alloy steels, if you see with the A6633 grade E, you're having a tensile strength of 520 and yield strength of 380, and what is the ductility? It is 23. And if you see the application structures used at low ambient temperature, now see here, at low conditions, at low ambient temperatures structures, if you are working, then you have to go with this type of A633 grade E type of steel. And if you want to go with the other A656 grade 1, the tensile strength is 655 megapascals, yield strength is 552, and the ductility is 50. And if you see the applications, what you are having, truck frames and railway cars. So like that. So any railway type of applications are there and truck cars are there, then you have to go with this A656 grade 1 steel. So like that, these have been the plain as well as high low carbon steels have been classified. That is about low carbon. Now coming to the medium carbon, that means in the low carbon you are having very less than 0.25% of carbon. Now coming to the medium carbon steels, what we are having here, the medium carbon steels have carbon concentration between 0.25 to 6.68%. So this is the range you have to know. So in the low carbon you are having below 0.25%. Now coming to the medium, it is in between 0.25 to 0.608% of carbon. So any alloys lying within this range, the carbon concentration, then those type of steels are called as a medium carbon steels. So these alloys may be heat treated by austenizing, quenching, and then tempering to improve the mechanical properties. But the low carbon, it is not responding to heat treatment. That's why we are going with the low cold treatment process. But this medium carbon, they are responding to heat treatment process. That's why with this heat treatment process like quenching and austenizing temperature it is reaching, then at those temperatures we can add some alloys to improve the mechanical properties. So they are most often utilized in the tempered condition, that means at high temperatures, which is having the microstructure of tempered martensite. So like that, these are responding to heat treatment process. That's why it is very easy for us to improve the mechanical properties when you compare with the low carbon steels. And the plain medium carbon steels have low hardenability and can be successfully heat treated only in very thin sections and very rapid quenching rates. So at high rate of temperature, but very quick rate of time, and for thin type of material, you can do this quenching process. Addition of chromium, nickel, molybdenum improves the capacity of these alloys to be heat treated. So that's why, if you see here, addition of another alloys like chromium, nickel, and molybdenum is improving the mechanical properties. So in the low carbon, we have another type of alloys. Medium carbon, you have another type of alloys. So depending upon the material also, the alloys should be varying to check whether the properties are improving or not. So like that, a lot of research is going on by adding some alloys into the base material to enhance the mechanical properties. So in this case of medium carbon steel, we are adding chromium, nickel and molybdenum to improve the mechanical properties. So because of those, what is happening here? There is a increase in the strength as well as the ductility here. So in this case, since you are adding some alloying element, what is happening? The strength as well as the ductility is improving in the medium carbon steels. And these are heat treated alloys are stronger than the low carbon steel. So when you compare with the low carbon, of course, these are having a stronger value of strength. So that's why these are very, very stronger than the low carbon steels, but a sacrifice of ductility and toughness. So these values are less compared to low carbon steels. So each individual is having its own properties. So depending upon these properties, we are trying to differentiate what are the advantages, what are the disadvantages when we compare the properties. And applications include railway wheel trucks, gears, crankshaft and other machine parts which are having high strength structure. So this is very, very important. So wherever the high strength structural components are being done, so these can be done with the medium carbon steels. So like that, you have to identify based upon the applications. And again, high strength, wear resistance and toughness. These are some of the other properties where we can improve the quality of the component. And coming to the high carbon steels. So what are the high carbon steels here? So again, you have to differentiate the low, medium and high based upon the carbon percentage. Now in this case, what is the range of the carbon percentage here? 0.6 to 1.4 weight percentage. So this is the range where the high carbon steels have been there. So here the carbon steels are having the carbon content generally in between 0.6 to 1.4 weight percentage of carbon, and these are very, very hardest, stronger and least ductile of the carbon steels. So because of the increase in the composition of the carbon content, in this case you are having the hardest and strongest material. Of course, the ductility is very, very less, and these are almost always used in hard and tempered conditions. That means at high temperature conditions, these type of high carbon steels are being used. Medium and high carbon steels are used in a high temperature conditions, but low carbon steels are being used in a cold working process. And since these are using at high temperature conditions, so these are especially wear to resistance, capable of holding sharp cutting edges. So because of that, what is happening? The applications are being changing. So because of that hard working and hard temperature conditions, these are specially wear resistance. Okay, they can withstand to wear as well as it can hold sharp cutting edges. So these are some of the applications where these high carbon steels can be used. And the tool and the die steels are high carbon alloys. So what are the cutting tools are there? The dies are there. So these are all manufactured with the high carbon alloys and using containing the chromium, vanadium, tungsten and molybdenum. So again, some alloying elements are differing in this case also. So in the high carbon steels, if you add the alloying elements like chromium, vanadium, tungsten and molybdenum, what is happening? Again, we are trying to increase the properties of this high carbon steel. So because of these alloying elements, what is happening? It is very, very hard. It is becoming, the metal is becoming very hard, and it is resistance, wear resistance is improving because of that carbide compound. And these steels are utilized in cutting tools, dies and forming of shape material as well as knives, razors, hacksaw blades, springs and high strength wire. So what are the applications are there here? This is quite different from the low carbon as well as the medium carbon steels. So in this case, since we are using the percentage of carbon is very, very high, as well as the composition, whatever the composition we are using like tungsten and molybdenum, what is happening? The applications are becoming very wide when you compare with the low as well as the medium carbon. So in this case, because of these alloying elements, what is happening? You can use these high carbon steels in a cutting tool as a cutting tool. So what is the application of a cutting tool? We can do any cutting process with the help of this cutting tool. Sharp edges can be manufactured with this, as well as different shapes can be formed with the help of these high carbon steels. And also the daily needs like knives, what are the knives we have, razors, all these can be manufactured with the help of these high carbon steels. So these are some of the applications where these high carbon steels have been classified. And coming to other type of steels, we have these stainless steels. So stainless steels are highly resistant to corrosion. So corrosion is very, very important. So any material which is resistant to corrosion, then that is very, very useful and it is having a good life. So it has to avoid the rusting formation. So how to avoid the rusting formation means the material has to be alloyed to some alloying element, so that though it is exposed to different environmental conditions, that has to be withstand. If it is exposing to some environmental conditions, cold or hot, even the chemical exposure, so those material has to be withstand. That means it has to be resist to the corrosion. So these stainless steels are, most of the stainless steels are very, very high resistance to corrosion. So a wide variety of temperatures or at ambient temperatures, these are being withstanding. Their predominant alloying element is of chromium concentration of at least 11% weight. So if any material is having at least a minimum 11% weight of chromium, then these are withstanding to resistance. So like that, the variation of percentage of alloying element improves the mechanical properties. So if you want to increase the corrosion resistance value, then at least minimum 11% weight of chromium should be added for these steels to get as a stainless steel or to get as a highly resistance to corrosion. And corrosion resistance may be enhanced by nickel and molybdenum additions also. So apart from these 11% of chromium, if you add nickel as well as the molybdenum in this, it will also improve the enhancement in the corrosion resistance value. So these are the things what we have to identify. So any material, if you are selecting for the manufacturing process, and this material has to be exposed to some different climatic conditions. So for those different climatic conditions, the material has to be withstand. So how do it withstand? That means you have to add some alloying element to that base metal, so that though it is exposed to different climatic conditions, this can be withstand. So like that, 11% minimum, there should be 11% of chromium in that steel, so that it can improve the corrosion resistance value. And rather than this, if you add some nickel as well as the molybdenum additions to that, the corrosion resistance value also increasing. So these are the things you have to remember when you are classifying any type of steel based upon the compositions. And coming to the other things what we have in the ferrous materials, we have cast iron. Again, the cast iron is ranging in between 3.0 to 4.5 weight percentage of carbon. So every type of material based upon the composition only. It is not based upon any other things. Based upon the compositions only, we are trying to classify what type of iron it is. So if we have seen the previous sessions, based upon the compositions, it is a low, high or medium. And depending upon those compositions, what are the properties and what are its applications. Like that, for each and every individual, we have these things. And at what temperatures we are getting? Generally, we are getting at 1150 to 1300 degrees centigrade. So all these things are based upon the iron carbide diagram. From the iron carbide diagram only, we are trying to extract the values of these materials. We are trying to get the compositions with respect to temperature. So like that, again, these cast irons have been classified. And generally, these cast irons are having decomposing with respect to the temperature. It is being decomposing into different types of elements, like you are having here ferrite and graphite. So if you increase the temperature, the carbide content is being decomposing into two elements. So these are the extensions. So in the previous sessions, we have discussed only about the carbide content. So where we are getting carbon content at this point at 6.708%, we are getting the carbide Fe3C. But beyond what is 6.7370, we have not seen. So if you go further up to 100% compositions, we are getting graphite. So if you want to have any graphite compositions, we have to cross that limit. That is, what is the limit? Maximum limit 6.7 weight percentage. If you cross this 6.7 weight percentage, then we are getting 100% weight. We are getting the graphite. So if you want to use the graphite compositions or graphite material, you have to go up to 100%. So that is what we can identify. We can extract the values from the iron carbide diagram. So again, that iron cast iron, again, it is divided into different categories based upon the microstructure. So here the cast iron again is kind of changed into grey cast iron. So what is grey cast iron again? It is subclassification based upon the composition. So what are the compositions here? 2.5 to 4% of carbon content is there, and 1.0 to 3% of silicon is there. Then that type of component is called as a grey cast iron. Okay, 2.5 to 4% of carbon and 1 to 3% of silicon compositions are there. Then that type of material is said to be a grey cast iron. And why this grey means, you can observe some black patches here. So these are in the form of a flakes, the cornflakes, whatever you're seeing, it is in the form of some flakes, and this color is in the grey formation. So that's why it is called as a graphite flakes or grey carbon iron. So like that, the grey cast iron. So like that, you are trying to differentiate by help of the microstructure. So this is one of the classification of the cast iron. And if you see the mechanical properties, it is having very weak in brittle and in tension. When a tensile force is acting, this type of grey cast irons are very, very weak. And the tips of the graphite flakes are very sharp and pointed, and these can be used in the cutting process. And again, strength and ductility are much higher under compressive. So just opposite, when you are giving a tensile force, it is having very, very less value of brittle in nature. But for the same material, if you are giving a compressive force, what is happening? The strength as well as ductility is being improved. So that is what the difference you have to identify between the compressive and tensile force when applying on the grey cast iron. And again, if any type of machinery is happening with some vibrations, so in order to control those vibrations, you are going with this type of grey cast iron. So when you compare with the steel and grey cast iron, so this A graph indicates with the steel manufacturing products. So these are having a heavy damping force, that is, it is happening huge vibrations during the working process. So suppose the same material, if you are making with the graphite, grey cast iron, so the damping or the vibrations are being controlled. Almost 50% is being controlled. So up to this point. So all these damping forces or the vibrations are being controlled when you are using the grey cast iron. So like that, depending upon the applications, you have to select the material. And coming to the white cast iron, again, if you are any containing less than 1% weight of silicon, then those type of category comes under the white cast iron. And why this name means, so you can observe some white patches in the microstructure, and these white patches are surrounded by with these dark things. These are called the pearlite. Okay, so it looks like a white thing, so that's why it is called as a white cast iron. So whatever the white area is there, this is being surrounded with the pearlite. So this type of category comes under the white cast iron. And if you see the limitations and applications of this white cast iron, it is very, very hard and wear to resistance. So these are some of the good applications or good properties what we can have, and without high degree of ductility, for example, in rolling. So in the rolling process, when you want to do any sheet rolling, if you want to decrease the diameter of any huge sheet, we have to use some rollers. So these rollers are being manufactured with the help of white cast iron, since it is very, very hard and wear resistance. So because of these properties, we are using for this rolling application. So like that, we have to classify or we have to differentiate based upon the composition, the applications and the properties. And coming to other type of white grey cast iron, you have malleable cast iron. So in this again, you have the in between the white cast iron and grey cast iron, you are getting this malleable cast iron. So this is the intermediate product of the grey as well as the white cast iron. So based upon the microstructure, it is very easy for us to identify, and it is very easy to characterize the given material. And if you see the different compositions or different mechanical properties, so what you are having here, you are having SAEG 1800. So this is one of the grade you have in the grey cast iron. So again, the grey cast iron is being classified based upon the compositions. So if you see the small variations in the compositions, you are getting different types of application, as well as the mechanical properties are also varying. So small change in the composition of the carbon content or silicon content or magnesium content. So the grades have been again giving some different grades to identify those, and these grades will give us the values of the mechanical properties, and always because of these mechanical properties we are getting some applications. So if you see the SAE G4000, so you are getting 276 tensile strength, and if you see the applications we can use in the diesel engine castings, liners, cylinders and pistons. So what are the automobile, some of the components are there. So these some of the important components are being manufactured with these type of grey cast iron, that is SAG 4000. So like that, if you want to have the microstructure of that, you have the complete pearlite structure. So like that, each and every type of cast iron has been classified based upon the properties, based upon the mechanical properties, based upon the compositions of different alloying elements. So like that, you have for ductile material, malleable cast iron, graphite iron. So each material again classified based upon the compositions. Coming to the non-ferrous. So non-ferrous alloys are nothing but which are not based upon iron content, which are having very less percentage of iron content. Then those types of elements are called as a non-ferrous elements. So generally steel and other ferroalloys are very easily consumed because we are getting in a large quantities. They are very available. So based upon the wide mechanical properties, we are trying to use those things. But what are the drawbacks? What are the drawbacks here? So it is very limitations for high density. So you have very high density. Because of that high density, your weight is very high, and low thermal conductivity. So these are some of the drawbacks what you have. And one more thing is it is corrosion. So it can't resist to corrosion. So these are three drawbacks. So because of these drawbacks, we are going with the non-ferrous alloys. So for many applications, it is advantageous or even necessary to use other alloys that may be suitable for the property combinations. So different types of alloys we can add based upon the non-iron content, and we can improve the qualities or we can improve the mechanical properties, and we can use those things. And these are again characteristics characterized into group of alloys. So you have different types of non-ferrous like copper and its alloys. So these copper and copper-based alloys possess desirable combination of physical properties, and they have been utilized in quite a variety of applications. So what are those applications means? Because of this having a good wear resistance or corrosion resistance, including ambient temperature, and for the different types of chemicals also it cannot be reacted. These types of copper and its alloys are being used, and the main thing is corrosion resistance. Based upon the corrosion resistance, the mechanical properties are being improved or being enhanced. So the most copper alloys cannot be hardened or strengthened by heat treatment process. So you have the cold working process and hot working process. So in this case, most of the alloys which are using in the copper cannot be hardened or strengthened based upon the hot working process. So we can do with the help of the cold working process, and we can improve the mechanical properties. Now when you see the ferrous elements, there we can do the enhancement in the mechanical properties by hot working process. But in case of non-ferrous alloys, you can't do or you can't improve the mechanical properties with the hot working process. So we are going with the cold working process to enhance the or to improve these mechanical properties. So that is what we are doing in the non-ferrous alloys. And most of the copper alloys are the bases which are for zinc as a substitutional impurity to increase the mechanical properties. And these are again some of the different types of alloys what you have. Again, based upon the compositions, these are being classified, and based upon these we have some different mechanical properties like tensile strength, yield strength and ductility, and based upon these again we have different applications. So like that, each and every non-ferrous element is being classified depending upon its composition. So one example, if you see here, phosphorus bronze, it is again having some unique number, and what are the compositions you have? 5% of silicon and 0.25% of phosphorus, like that. And it is done under cold working process. It is not being done in hot working process. And if you see the tensile strength, you are having 325, yield strength is 130, ductility is 64. And what are the applications are clutch, discs, fuse, clips, and springs. So all these are some of the important, very, very important parts in the automobile engineering. And another type of category is aluminum, copper, and the second one is aluminum and its alloys. And again, these are classified based upon the compositions. So these are having very high electrical and thermal conductivities. So thermal conductivity should be very, very high in any type of metal working in high conditions. So, and again, this is high resistance to corrosion. So like that, we are trying to increase the properties when you compare with the ferrous alloys. So these are very, very important for us to increase the properties. So that's why we are going with the non-ferrous materials. And again, what are the applications you're having here? High ductility. It is having high thermal conductivity, high electrical resistance, as well as the high thermal conductivity. So like that, you can use these things depending upon the application. So what are the list we have discussed in the previous slides? So based upon those mechanical properties and applications, we can try to use those grade differentiated alloys. And the mechanical strength of aluminum can be enhanced by cold working. So all these non-ferrous are being enhanced with the cold working process only. So when you compare with the ferrous alloys, we are doing with the hot working process. But when you comparing with the non-ferrous, all these mechanical properties can be enhanced with the help of the cold working process only. So again, if you add some other alloying elements like copper, magnesium, silica, you can still increase the properties. So for every type of base material, there are some alloying elements to enhance the mechanical properties. So with these properties, the applications are being varied. And these are some of the different types of mechanical properties with respect to composition and the typical applications what we have. So if you see with the 5052 type of wrought iron, so here you have 2.5% of magnesium and 0.25% of chromium. And this is improved with the strain hardening process with the cold working process. And you have tensile strength of 230, yield strength as 195, and ductility ranges between 12 to 18. So where can you use this type of material is in aircraft fuel and oil lines, fuel tanks, appliances, rivets, and fires. So these are some of the applications. So like that, the compositions are very, very important for us to describe all these things. And these are other type of materials. In this cast heated alloys are there. Again, you have different types of compositions which is being heat treated. Then you're getting 0.228 tensile strength of megapascals, 164 megapascals of yield strength, and ductility is varying. And again, so most of the aircraft in applications, we can use these type of alloys to improve the mechanical properties. So the last one is the titanium. Again, these type of titanium are very, very new to the engineering materials and possess an extraordinary combination of properties. So compared to the aluminum and copper, these titanium is having more improvement in the properties. So like that, different materials are coming based upon the compositions what we are adding. So here we are getting a high melting point. So up to 1668 degrees centigrade, that is the melting point of the titanium, and the elastic modulus of this is 107 gigapascal. So that is a high value when you compare with the any type of non-ferrous alloy. And it is having very extreme strong at room temperature. The tensile strength is very, very high, approximately 1400 megapascal. So like that, you are increasing the properties by adding some alloying elements. So there is an improvement in all these things. And these can be highly ductile and easily forged and machines. So like that, you have some different applications based upon those elements. And these are having a hexagonal closely packed type of microstructure and 883 degrees centigrade. This HCP metal is transforming to alpha beta phase. So when it is reaching that melting temperature, then it is changing its phase from one phase to other phase. So that is a transformation which is being happening depending upon the temperature. And the major limitation of titanium is it is very chemically reactive with other materials. So that is what you have to identify. And because of this, you have to restrict your applications. And it is very, very corrosive resistance of titanium at normal temperature. So at normal temperature, it is very reactive to the corrosion resistance and virtually immune to air marine, and variety of industrial environment. So all these things you have to identify, and you have to restrict your application depending upon those properties. And again, these are some of the mechanical properties list what we have. If it is at alpha phase, so the HCP is converting to beta phase, alpha phase depending upon the temperature. So when it is converting into from one phase to other phase, so here the composition is also varying. So if the composition is varying, it is being annealed. That means at high temperatures you are doing your listings, and the tensile strength is 826, yield strength is 784, and ductility is 16. And if you see the applications in gas turbine engines, casting rings, chemical processing equipment, we are using these type of alpha type of phase of these titanium alloys. So like that, you have to identify how the phase is changing with respect to the temperature in case of titanium alloys. Based upon the phase change, what are the compositions you have to identify using the tri-line method. And from the tri-line method, you can identify what are the mechanical properties. And from these mechanical properties, what are the typical applications you have to identify. So this is about the ferrous and non-ferrous alloys and its applications and the properties. And based upon these things, how we are applying the ferrous as well as non-ferrous materials to the required application. So from the introduction to physical metallurgy, essential of material science engineering, metals is science and engineering, material science and engineering. These are some of the references where you can get the information of today's ferrous and non-ferrous material topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.